Okay, good afternoon. We continue our discussion of support vector machines. Let me just remind you a bit. So the support vector machine is a binary perceptron that we train such that the separating plane has maximal margin, maximal distance, maximal minimal distance to any point among the points that we're trying to classify. So, we could have this example, and the margin would be the distance to the closest point. That's what we're maximizing. And we concluded last time that the weights can be written as a combination of the examples. And moreover, they're typically, the weights that achieve this goal are typically a combination of a very small number of points, and these are the points that end up being at the minimal margin. So we saw also that alpha mu times 1 minus y mu w transpose x mu is equal to 0, meaning that either the point has minimal margin. We already work with weights such that the minimal margin will always be 1. So let me write that as well, that y mu w transpose x mu is at least as large as 1 for all mu. So either the weights are such that we're at minimal margin, and if it's not, if it's a point which is further away, then alpha mu is equal to 0. And all the alphas are positive, or 0. Okay, these are the properties of the solution that we found. And we found also that alpha mu, if you want to find them, we need to solve a p-dimensional problem, and that's the dual problem. They maximize q of alpha, which is sum over mu, going from 1 to p alpha mu, minus half sum over mu and nu, alpha mu y nu, x mu transpose x nu. This we also called k mu nu. You have all this in the notebook, so I'm just doing it because we'll use it, but you don't necessarily need to copy this. Under the constraint that all the alpha mu's are non-negative, and this is called the dual problem. Okay, so now what I need to finish is the proof of the convergence of the Adatron algorithm, which solves this problem numerically. So I will do it quite quickly, just to finish this. The idea of the proof we discussed. What we're going to show is that at any step of the Adatron algorithm, q increases, and because q is a function which has a unique maximum, even with a constraint, it doesn't have local maxima. This you can see geometrically from how it's constructed. I drew it last time. It's kind of it's a paraboloid in three-dimensional space with some constraints which are cutting it, but it won't have local maxima. So if q is increasing all the time, it has to approach the maximum. The maximum is not the top of the paraboloid because of the constraint, but it's somewhere, and we'll show that this maximum is the solution. So the Adatron algorithm, what it does in each step is, I'm writing it now briefly. We cycle through the examples nu. We update the alpha corresponding to the example nu as follows. delta alpha nu is the maximum of minus alpha nu, which just ensures that if the change is negative, alpha nu will not become negative. And eta times 1 minus delta nu. Okay, and delta nu is y nu w transpose x nu, where we all the time we take w to be this thing. All right, so now the next thing that we showed is that delta q can be written as delta alpha nu times 1 minus delta nu minus half delta alpha nu square x nu, right? And now we discussed two cases. The first case is that 1 minus delta nu is positive. And then we showed that, and then we just plug in, if it's positive, then it's equal to this, necessarily. This is then larger than this. So if we can, in any case actually, where we can we know that delta alpha is this quantity, we can just plug it in, and we get that delta q is y minus delta nu square times eta minus half minus no, sorry, we have an eta here. I'll put the eta here. So we'll have 1 minus eta. Here we have two etas because delta alpha nu contains eta square. One of them I put here, x nu. This is positive. And I assume that eta is sufficiently large that for all the examples, this is also positive. It's sufficiently small that for all the examples, this is also positive. So this is, this is positive. What we are left to do is to take the case of 1 minus delta nu smaller than 0. In that case, there are two possibilities. One is that still this is larger than this, and actually this applies, what we did here. But the real problem is the case where, or the different situation is the case where this is the larger quantity. But what we can always say under this condition is that that eta times 1 minus delta nu that delta alpha nu is at least as large as eta times 1 minus delta nu, right? Because it's the maximum of these two quantities. And therefore, 1 minus delta nu is at least as small as delta alpha nu divided by eta. And the reason is that under this condition, delta alpha nu is negative, right? So, sorry, here I just used this. Sorry, here I just used this. But now I will use the fact that delta alpha nu is negative. So if this is true, that 1 minus delta nu is smaller than this, I'm going to replace 1 minus delta nu with delta alpha nu. Last time, my mistake in the proof that I tried to do is that I tried to replace delta alpha nu by this inequality by 1 minus delta nu, and then it didn't work. We're going to replace this by delta alpha nu, and the sign flips because delta alpha nu is negative. So what I have now is that delta q is at least as large. Again, here we have smaller than, but it's multiplied by something negative, so it's at least as large as delta alpha nu square divided by eta. And here we have, so this is this term, and then we have, the regular term that I'm not going to touch, delta alpha nu x nu. And we can just take, the eta, 1 over eta outside, and delta alpha nu square outside. And we see that this is multiplied. This is different from here, but it's multiplied by the same quantity, 1 minus eta over 2 x nu. And we assume that this is, eta is sufficiently small, that this is positive, this is also positive, so it's positive. So one thing to note, in somewhat differently from the proof of the perceptron learning algorithm. In the perceptron learning algorithm, we were able to show that the function that we're trying to optimize changes sufficiently fast in each example that it has to, we didn't try to optimize the function, but we found that there's a function that increases each time, and it's bounded, and it increased sufficiently fast that we could conclude that the algorithm converges in a finite number of steps. Just a moment. This was the perceptron algorithm. The perceptron algorithm doesn't really need to find one very particular solution. There are many different solutions, and it just finds one of them, and it does it. The Adatron algorithm, you can see here that even though the changes are positive in each step, they become smaller and smaller. At least the bound that we found becomes smaller and smaller as we approach the true solution, because the delta alpha nu's become small. 1 minus delta nu also becomes small. And so this algorithm doesn't converge in a finite number of steps. But what we can conclude from the fact that delta q is positive in each step is that it must approach some steady state solution, which maximizes this form. And actually, the very fact that it reaches a steady state solution, we can conclude from it, I will answer a question in a moment, we can conclude from it that it's a solution of the problem. And so I will just write this down very briefly. Sorry. So actually, maybe we'll stop for a moment and I'll take the question.
How do we know that it converges to the global maximum, not to a local one?
Okay, so first of all, this problem does not have local maxima.
Why?
Well, this is because of the geometry of the structure of the function that we're trying to optimize. What is it? It's a paraboloid. A paraboloid has just one maximum. That's not really the maximum of the problem usually, yeah. But we're cutting it, with these planes which are the constraints, and this kind of problem doesn't have local maxima. And so how do we know that we're actually converging to the maximum? The argumentation is, we know that we reach a steady state, we approach a steady state solution, and now we can see what are the properties of the solution. So we know that the alphas go to some fixed point. What can we say about this fixed point? We know that all the deltas are at least as large as 1, because otherwise we would increase the alpha nu, right? Our algorithm would increase the alpha nu if they weren't. We know, on the other hand, that alpha nu star times 1 minus delta nu star has to be 0, because otherwise we would decrease. We know that all the alpha nu stars has to be positive because we keep that property throughout all the steps that we do, and we also know that that our weights, they are not explicitly written here, but we're using them in each step based on what I wrote there. So we know that all the weights obey that there are sum over mu of alpha mu star, y mu, x mu. So these are really the conditions that we wrote earlier. We discussed the fact that these conditions are, if we find a set of W's that obey these conditions, it's a solution of the problem. And also, our argument was that we know that we reach steady state solution that has to be the maximum. We increase at each step, so we have to approach the maximum. Okay, so this concludes what I wanted to tell you about the Adatron algorithm. Any other questions?
Can you repeat the second, the one we got confused in last time?
Gal, right?
Yeah.
Okay. So which step?
The the second step.
Okay. So the difference between what I did today and what I was trying hopelessly to do last time is that in this case, instead of trying to replace the delta alpha nu by something proportional to 1 minus delta nu using this inequality, I replaced 1 minus delta nu by delta alpha nu using this inequality. Okay, and that allowed me to get an equality of at least in the right direction, because this is at least as large. This is smaller than this, but it's multiplied by something negative. So the product of this and this is larger than delta alpha nu square over eta. Okay? If I would try to replace delta alpha nu by 1 minus delta nu, which is what I tried to do last time, this is larger than this, but I'm multiplying it by something negative, so I flip the sign of the inequality, and I don't want that. I want to prove that delta q is at least as large as something.
So it's also when multiplying by delta alpha mu, it's negative.
Doesn't matter. What I want to show is that delta q is larger than something. So I have here something negative multiplied by something negative.
Okay.
This something negative is smaller than something. The product is larger than something, which is so. This, we know that this is positive, but we want to show that it's sufficiently positive. Okay. So last time, in this case, we replaced the delta alpha nu by we replaced the delta alpha nu by something and replaced it also here. In this case, we replace this by delta alpha nu and we leave the delta alpha nu here as it is. So that's why the prefactor here is different in this case and in this case, but in both cases it's positive. Okay. Another question?
Yeah,
Alex?
Yes. You say that it's not exactly convex optimization, that there is no maximum, but
No, it is. I didn't say that it's not a I didn't say the word that
there is no maximum in the. You can find the maximum in the problem.
No. I said that the maximum is a global maximum. It's not the maximum of the paraboloid.
Yeah. Okay.
That's all. But there is a maximum. There is one global maximum to this problem. And the term that you use, the fact that it's a convex optimization problem, is true. It is a convex optimization problem, and that's why it's not a hard problem.
Proving that delta q is greater than 0 in bounded, you just know that it converges, but how do you know that it converges to the maximum?
Okay, so I used another argumentation here, which is using the fact that I know that all these by the fact that it has converged, I know that for the fixed point that it converges to all these properties hold. Okay, and then I know that this is the solution of the problem. Okay. Okay, so now the next topic that we going to discuss about is called the kernel method, and it's a very beautiful idea. Before maybe I will keep this. Before I discuss the kernel method, let's just overview a little bit what we've done so far. So we discussed the binary perceptron, and we saw, just for random patterns, what can we say about conditions under which what is the fraction of dichotomies that can be realized, and we saw that if the number of the examples is sufficiently small, then we can always find a separating plane, assuming that the examples are in a general position. We can always find a generating plane that will solve the problem. And then we discussed the support vector machine, which is really a situation where, relevant to a situation where the examples are not random, the categorization is not random. The whole motivation for maximizing the margin is the thought that close by examples are probably classified similarly, and therefore we don't want our plane to be very close to the example, because then there will be another point which is very close by which will be classified differently from an example, and that's unlikely. So we use the motivation for using the support vector machine is the assumption that there's continuity in the function that we're trying to approximate. However, if we stay, in 2 dimensions, for example, and we have more and more examples, it's clear that we will not be able to find a separating plane because, typically the situation will be that, there's certainly no guarantee that we will be able to find a separating plane. And typically, many functions cannot be, categorized using a linear plane. So, for example, in 2 dimensions, green will be +1 and okay, I don't have another color. So this would be -1. So, we could a separating surface might look like this, but it's not a linear. You cannot find a hyperplane that, or in this case, a line that categorizes these examples correctly. So the idea in the kernel method is to take our examples. Maybe initially our examples are low-dimensional. Our vectors are low-dimensional. Take our vectors and embed them in a higher dimensional plane. Okay? So imagine that we have n dimensions. Embed them in a higher dimensional plane. That's called dimensionality. The dimensionality M. Now, we can, if the dimensionality M is sufficiently large, and if we choose appropriately our embedding, then we have a chance, then the number of points will be much larger. Maybe the dimensionality will be larger than the number of examples. And then if the points end up being in a general position, we know that there is a separating plane that is going to categorize them correctly. So that's the idea. And then we're going to apply the support vector machine. So in a bit more detail, if I draw this graphically, we have our points x1, sorry, not our points, but our inputs x1, xn. These are the coordinates of each one of the each one of the points. So now, the indices are the indices of the example, and we want to translate this vector to an m-dimensional vector. So the idea is that we will have a set of functions Each function is a function of all the x's. Okay, so we have m functions. And so phi I of x is some function. And I will already write that it's a nonlinear function of x. And so this is, by definition, a transformation from Rn to Rm. And again, we're going to apply the support vector machine on these vectors. That's the idea. There are many different ways to choose the functions. We'll discuss this a bit later on. Yes?
Okay, but then if we do everything, we will go in the n-dimensional space, apply the support vector machine. What do we have? We have a separation hyperplane in an m-dimensional space.
That's right.
So what's the...
So now, okay, so now...
So we don't have anything, we don't have this kind of circle.
Well, implicitly you do, because for any n-dimensional vector that you will give me, other than the set of examples, you can still do the same translation from that vector to the m-dimensional vector, apply the support vector, apply the categorization that we found. So we will find a categorization in m-dimensional space which involves an n-dimensional set of weights. And this is a categorization in the n-dimensional space. In the m-dimensional space, it will look like a surface. In the n-dimensional space, it might have some curved. The separating surface is some curve.
And we can also do it with an example, with an unknown example. Like take another.
Yeah, but this is what we do always with, even when we discuss the perceptron without doing this trick, you know, we had a set of examples, and then we hoped that we have a good approximation for the function. We can apply it also to some other examples, and it will categorize them, generalize well. That's our hope.
Okay, which I don't have like, I'm not imagining. I just have the two-dimensional space. Let's take a three-dimensional space.
Yeah.
I can just give the green points like additional depth, so they're sticking out, and the black points additional depth in the other side, and then I can cut separation between the black and the green points in the three-dimensional space.
That's right.
Very nice. But every other point, so what do I give any depth towards the board or towards the classroom then? If I have a new point, what kind of depth in the third dimension?
Well, you have a rule for each point in the two-dimensional space. You have a rule how to categorize it. You translate it to the three-dimensional space, and you ask whether it's on one side of the plane or on the other side of the plane, and that's a categorization in the two-dimensional space.
Okay, so phi is independent
is a fixed function of the x's.
Yes, but it's not of the categorization without knowing.
That's right, exactly. The function phi is not something that we're going to touch. That's a very important point. The only thing that we're going to choose it based on some, you know, heuristics. People know that certain functions work well. There are some other considerations that we will discuss a bit later on, but that will be fixed. The only thing that will optimize in the higher dimensional plane is the weights.
Okay, so phi doesn't know where the point, in which category the point goes.
P?
Phi, is it phi?
The phi, that's right, exactly. Yes. Are you off?
No, I just like got the same question. I mean, if you did know like what category you could just have m equals n plus 1, and then like all the just make phi like give the left coordinate the label.
Yeah, of course. So we're not allowed to do that. The rules of the game are that there is some transformation, and we did it because we hope that in the higher dimensional space, our examples will be linearly can be separated by surface. Now, the beauty of this idea is, as you'll see, this will now need to develop, is that it's in some sense much more simple than it seems. It seems like, you know, if phi is very high dimensional space, we need to solve a very high dimensional problem. We need to solve the, you know, optimize m weights instead of optimizing n weights. But through the dual problem, this is not the case, because remember, in the dual problem, we always just solve a p-dimensional problem, right? The number of support, the alpha, as a number of examples. So if the number of examples is smaller than the dimensionality, and that's typically going to be the idea here, we're not really losing we're going to solve a p-dimensional problem and not an m-dimensional problem. And the way we do it will turn out to be very elegant. So, but before we discuss that, let me just give you some example for a transformation. So this is really just one example. The vector phi of x might include, you know, the coordinates of x themselves, and then maybe all the products of two coordinates. So this is this part is nonlinear. So we could have x, you know, x1, x2, you get the idea, up to xn squared. That's a legitimate choice. What is m in this case? Yes? Did someone ask a question?
You're doing multiplications every time there's an interval?
Yeah, it's all the combinations. x1 squared, x1, x2, x1, x3, all the combinations. So what is m in this case? So first of all, there are all these. So this is n plus n times n plus 1 over 2. Now, why did I write down that this function is nonlinear? Why is it important? Right. So, if this function is linear, then in the end, once we take the linear combinations of these functions, we're still implementing some linear function of the x's. So we can't gain anything from that. It's obvious. Any choice of weights of phi's here, which are linear functions of the x's, there's no possibility that we'll gain anything from that, because in the end we'll be implementing a linear function of the x's. And so our only hope can come from the fact that the phi's are nonlinear, and then it could be that a problem which is, a set of points which is, for example, not on a general position, a set of x vectors which are not on a general position in this space will end up being in a general position in this space. So let's just write down now what we need to do. So one way to, if I suppose that I trained the weights on this space. So I have some weights. One way to think about it is that if I give you some new example, you will implement a function sine W transpose phi of x. Now, when I write phi with a vector, I mean a vector consisting of all these phi 1 up to phi m. So this is m-dimensional and this is m-dimensional. But I want to point out now that if we actually find the weight W using the dual problem, we can write this in a more simple way. So if we use the dual problem, if we work with the dual problem, we write the W as a sum of alpha mu, y mu, phi of x mu, right? Where mu goes from 1 to p. So what we need to calculate here when we try to calculate this thing, so let's call that y. Y is now the sine of sum over mu, alpha mu, y mu, phi transpose of x mu, of x, x mu times phi of x. So now I'm going to look at this quantity and I'm going to call it k of x mu and x. This is defined as phi transpose of x mu, phi of x. How do I calculate this quantity? X is some vector. So I give you some vector. X is an n-dimensional vector. I give you that vector, and I want to decide to see what is the categorization.
Okay.
So what do? I need to take this product, but I can write it in this way. So x mu is the n-dimensional vector corresponding to an example mu, and x is some new a point that I want to categorize using this support vector machine. Okay, so how do I calculate this quantity? So one way to calculate it is to translate, to go through all these phi's, to translate, the first x mu to the m-dimensional vector, to translate x into the m-dimensional vector, and then take the scalar product. But we'll often be able to choose problems in which we can calculate this product much more easily without going through to the m-dimensional space. And this is really going to be the beauty of the kernel method. That in many cases, we will calculate this function directly in n-dimensional space. we know that it corresponds to a scalar product in m-dimensional space, but we will not do it explicitly. We will not go explicitly through the n-dimensional space. So, so let me just write that y. For now, I will just write that y is equal to the sign of sum over mu, alpha mu, k of y mu, k of x mu x. This is what we need to implement whenever we want to categorize a new example. Okay? Now, what do we need to do to find the alphas? So to find the alphas, we need to apply the learning algorithm for the dual problem. And if we know how to calculate this scalar product easily, that helps us also in solving the dual problem. I will continue here because no, I can continue here. Okay, so so to find the alphas, we really need to maximize what we need to do is to maximize Q of alpha, which can be written as sum over mu alpha mu minus half sum over alpha nu y nu. And now what should be written here is the dot product of phi mu and phi nu, and the dot product of phi nu is k of x mu x nu. So again, if we know how to calculate this dot product easily without going explicitly into the m-dimensional space, we might be doing here a lower dimensional, n-dimensional calculation. You will see an example soon. And this is under the constraint that all the alpha nu's are larger than 0. And so we could apply the Adatron algorithm to this problem, and in the Adatron algorithm, we need to calculate at each step the deltas, and the deltas are written as sum over mu alpha mu y nu. Here we will have phi of x mu dot phi of x transpose dot phi of x nu, and this is sum over mu alpha mu y nu k of x mu x nu. So I want to repeat again. One way to think about it, that's very straightforward. We have this set of vectors, and all the time when we work with examples X, we translate them explicitly into the m-dimensional vectors, and we just apply the Adatron algorithm. We use the support vector machine in the m-dimensional space. But if we know, since all the expressions that we have involve these quantities, if we know how to calculate the dot product of phi of x mu, phi of x nu more easily, we might not need to explicitly go into the n-dimensional space. Here is an example. And with that, we will finish for today. So imagine that phi of x is the following vector. I will have one entry which will always be 1. That's a nonlinear function of the coordinates. Okay? And then I will have the other elements of I. Will be just, the elements of x up to the square root of 2, which I'm writing here for convenience. And then we will have all the x's squared, x2 squared. So this is very similar to the examples that I wrote before, except for the prefactors. You will see why they're helpful in a moment. And now all the mixed terms, I'll include also functions which are products of two different coordinates, but in these cases I will put a square root of 2 here. Okay, so, these are all the examples, all the products of pairs. Okay, so this is the certain transformation from n-dimensional space to an m-dimensional space, and m here is n plus n times n plus 1 over 2. This is like in the example that I shown before, plus 1 because I added also this function. Now let's see what is the product. Name? So finally I will have your name. How can you? R? Yes? Rui? Okay. Yes, so what is the question? So what is confusing you? What is the most confusing thing right now? So we have n functions which are just the linear ones, just the direct ones, and then we have all the combinations of two different coordinates. But I'm not going to count them twice. I'm not going to count x1, x2, and then I have another one which is x2, x1. So this is why this is n times n plus 1 over 2. All the combinations. Yeah. So sorry. Oh, that's right. This is n times n minus 1. Thank you. Actually, it's n times n plus 1 if I don't put the n. So I think you should correct also what I wrote. No one told me last time. That's right. We choose two different ones out of... sorry. No. But we also have these. No. But we have also these. We still have these. So this is n times n plus 1. Because we can choose the same one. If you want to choose two different ones out of n, it's n times n minus 1 over 2. But if you're allowed to choose the same twice, it's n times n plus 1 over 2. Okay? All right. So this is the dimensionality. And now, here's the nice thing. Let's see what is phi transpose of x times phi transpose of y. Times phi of y. So what do I need to do? I need to calculate the vector phi of x, calculate the vector phi of y, and then take the product, of each term. So here I will have 1 times 1. Here I will have square root of 2 x1 times square root of 2 of x2. So this will be 2 times x1 x2. X1 y1. And we'll have this up to 2 times xn yn. And now we will have x1 squared y1 squared up to xn squared yn squared. And then we will have 2 times x1, x2, y1, y2 plus all the other combinations. Now, if I look at it a bit more carefully, what we see is that what we have here is 1. If I take all these terms, this is x transpose times y. These are all these terms. And then, if I look at all these terms, what is that? Okay, so this is, I claim that this is a sum. I can write this as a sum over I and j xi yi squared. Why? Because there are two ways to choose
Won't it be the same?
sorry, xi yj squared. And then
Two times that.
yeah, so let me just see for a moment.
No. Isn't it the same in X and Y? Like the order you choose will be the same? Or is it like, it could be X1, X2, Y1, Y2?
So no, okay. So here these are all the terms where I have here the terms like this one. I have here x1 square, y1 square. So this seems like it should be
Like Y and X.
Okay, let me write down, and we will see why this is correct. So I have here this, and then I have here a sum over 2 times sum over I smaller than j, xi xj, yi yj. So these are these terms. And these terms,
Isn't it just like XI, YI? Because when
yeah, that's what I think. That's what I think. So
without the J.
without the j, that's what I think. That this is just xi, yi, and these are these terms. These are these terms. And then, okay, so this seems correct, right? All here it's always xi, yi square, and here we have, there's a 2, and it's always. Because I didn't want to count any combination twice, I always keep this index smaller than this one. So it's I smaller than j, xi, xj, and then in the y it's the same because it's always a corresponding one. x1 with x3 will go to with y1, y3. So this is correct. And I claim that this is the same as x transpose y plus 1 square. Okay, so what terms will we have when we calculate this thing? We will have the 1. We will have the mixed term, which is 2 times x transpose y. This is this. And then the square of this thing is really this thing. Okay? So, what we conclude, which I will write here, is that our kernel xy, k of xy, is simply 1 times x transpose y squared. So now you see an example where, explicitly, if we do everything in the m-dimensional space, we have this m-dimensional space. It has dimensionality n plus 1 over 2 plus 1. But every step of the adatron algorithm and the calculation of the categorization only requires us to calculate a scalar product of 2 vectors in the n-dimensional space. But instead of using, x transpose y, which is what we would do in the simple, directly in the support vector machine in n dimensions, we transform it to 1 plus x transpose y squared. Okay, and now this example can give us ideas for ways to expand to even higher dimensionality spaces. So for example, we could have chosen k of x of y, which is 1 times x transpose y to some power m, to some power d. We could write this object can be written as a scalar product in a higher dimensional space, even higher dimensional space than this one. So it's very easy actually to think of kernels that would correspond to a scalar product in some higher dimensional space. It can have huge dimension. And once it has huge dimensions and we have nonlinearities in here, it's likely that if we start with a set of P examples which do not lie in general position, we go to this very much higher dimensional space, and in that dimensionality of that space is larger than the number of examples, and they will lie in a general position. This raises a question that I will discuss in the next lecture, whether any function that I can, any function that can cook up or think of, if I generate some function of x and y that I decide on, does it always correspond to a scalar product in some higher dimensional space? If it does, then if we apply the support vector machine algorithm, we generate a support vector machine using the methodology that I wrote here, then what we're doing explicitly is calculating these functions, but implicitly we're training a support vector machine in some higher dimensional space. So we'll discuss that question next time. And for now, the TA session with Neta will also continue on the support vector machines. Questions? Okay. זה שם. חשבתי ששומרים את זה
מישהו שממש